Okay, so in this short video, we're going to talk about the alternating series. A quick example for the alternating series can be seen like this. You have 1 minus half plus third minus quarter plus 1/5, etc. As you can see that the sign in front of each term is changing, right? It's alternating. So that's the meaning of the alternating series. And also, the general alternating series representation, we would like to write the nth term an into this way. Often it's a -1 to the power n plus 1, and then un. Okay, where this un, as you can see, that is the absolute value of the nth term. In other words, this un is going to be non-negative. Okay, it must be greater or equal to 0. Also, as you can see that this series 1 minus half plus third, if we put an absolute value on each term, it then becomes into 1 plus half plus third plus quarter, etc. So we know that that series is a harmonic series. So for this series, we also have a specific name, which this series is called the alternating harmonic series. Okay, and all right. So that's about the meaning of a series. So now I'm gonna introduce a theorem. It's called the alternating series test. Okay. So alternating series test. So the test says like this. If we have a series given like into this way, and from 1 to infinity, -1 to the power n plus 1 un. Remember, this un is the absolute value of the nth term, which is the u1 minus u2 plus u3 minus u4, and then dot dot dot. Okay. So it says that this series, this alternating series, converges if the following conditions are satisfied. So 3 conditions here. Okay, so 1, we need to make sure that un are all positive. Okay, for all n. Okay, and 2, we need to make sure that un are eventually, okay, non-increasing. Okay, so in other words, we need to have un is greater or equal than un plus 1 for all the n is greater or equal than some integers. Okay, this capital N is some integer. So this capital N here is not necessary to start from 1. As long as it's a finite integer, it's good to go. Because the idea is, guys, even you have a, let's see, increasing pattern for the first n integers, but after that, you follow this pattern, and then, overall, the series might still converge. Okay, so that's why eventually, okay, not starting just from the first term. Okay, and then the last condition we need to satisfy is limit n goes to infinity. This is un, which is the the absolute value of the nth term must equal 0. Okay, so those are the three conditions for this alternating series test. Actually, it's very easy to apply because for the first one, un are all positive for all the n's. I would say 99.9% of the situation, this is already ready. Okay, so all we need to check is well, eventually un is non-increasing, and limit this un equals 0. Okay, so now let us maybe look at a very straightforward example, which we will go back to here. Let's look at this. Let's look at this alternating harmonic series. Okay, so we can write this down. So this series is n from 1 to infinity, negative 1 to the power n plus 1 over n. Okay, and so this is the series. Okay, so let's call this is example 1. Noticing that, guys, the corresponding un in this problem is 1 over n. Okay, and we know that un is greater than 0 for all n. Okay, n starting from 1. So first, easy to check. And then 2, I want to show that un is 1 over n. It is eventually non-increasing. As you can see that, guys, un is 1 over n, and un plus 1, it's 1 over n plus 1, right? So as you can see that this apparently this inequality holds, right? In other words, we know that un is greater than un plus 1 because this denominator is smaller, so overall this one it will be larger. So it is now increasing. In fact, it's not only non-increasing, it's strictly decreasing. Okay, so second bullet also satisfied. Third one, as you can see, a limit as n goes to infinity un, which is limit as n goes to infinity 1 over n, and apparently this is 0. Okay, so the third condition also satisfied. So from here you can see that this alternating harmonic series itself is converging. Okay, so series since it satisfy all three conditions from the alternating series test, that's short for EST. So series converges. Okay, converges. And from this example, I would like also to introduce one quick concept, which is called the conditionally convergent. Okay, conditionally convergent. And so for this example, as you can see that, guys, the series itself converges, but the absolute value of the series, it diverges. Okay, so under this situation, we call that this series is conditionally convergent. Okay, and from the previous lecture, we know that if the absolute value of series converges, we call the original series called absolute convergent. And if it's absolute convergent, it definitely converges for the original series, okay? But for here, we have a series. Itself is converged, but it's not absolute converged. So in this situation, we call that this series is called the conditionally convergent. Okay, so hope you enjoy this video, and thank you for the watching.